Today we're going to discuss expected values with a brief introduction to moment generating functions. You may or may not have seen this idea of an expected value of a random variable before. It's, in a certain sense, the mean value of a random variable that if, very simple example, you were to roll a die and define a random variable to be the value of the number on the die. Well, our intuition is that the mean value of this random variable should be 3.5 over the average of the 6 possible values that it can take on. And the expected value is just kind of a formalization of that particular concept. That if you roll a die, for instance, the expected value, the mean value, would just be you take the value of the random variable, which would be x in this case, times the probability of observing that particular value of x. So you roll a die, you would take 1 times the probability of getting a 1, which is 1 over 6, plus 2 times the probability of getting a 2, which is 1 over 6, plus 3 times 1 over 6, etc. If they're all equally likely, it just ends up being an average of the values. If some values are more likely than others, it ends up being a weighted value, but one way or another, you end up with what's, in a certain sense, the mean value of that particular distribution, and that's where this formula comes from. That for a discrete random variable, it's exactly what you would expect. You just take the value of the random variable times the probability of getting that particular value, then you add them all together. It's a bit more complicated for continuous random variables because obviously the probability of observing any particular value is 0. So we do the integration thing again. The intuition is that it's the value, it's a particular value times the relative probability of that particular value. Then you integrate over the entire thing. And in general, you don't have to find expected values of only the original random variable. You can also find the expected value of functions of a random variable that, say, for instance, you rolled the die and rather than finding the expected value of x, you wanted to find the expected value of x squared. Well, our intuition would be then you could take the probability of getting a 1 times 1 squared plus the probability of getting a 2 times 2 squared, etc., etc. This equation down here formalizes this, that if g of x equals x squared, then the expected value of x squared turns out to be just x squared times the probability of getting 1 squared times the probability of getting a 1 plus 2 squared times the probability of getting a 2, and so on down the line. And rather than using this formula for the expected value of a function of x, you could also just find the PDF or PMF of this variable y equals x squared, and then use the first definition. It turns out you'll get the same answer either way. There will apparently be a homework problem to show that later on. Anyway, here's a couple examples of expected values of continuous random variables. Say x is uniform on the interval a to b. It's equally likely to be any number between a and b. Well, as you'll recall, the density function for that particular distribution is just 1 over b minus a, the length of the interval. So we take the integral of x from b minus a, which work out the integral, that works out to be a plus b over 2, as we would expect it to be. If we have an exponential random variable with rate parameter 1, then the density, as you'll recall, is 0 for x less than 0, and for x greater than 0, it's e to the minus x. So we integrate from 0 to infinity of x times e to the minus x. The antiderivative is minus x times e to the minus x. And plus, I guess we're doing integration by parts here, I believe, is what's going on. It was a long time since I took calculus as well, and that ends up being equal to 1. And it's an important special case, the normal distribution. If integrate that, it's going to be equal to the integral from minus infinity to infinity of x times e to the minus x squared. It's density function for the standard normal. And I think there may be some way to find the antiderivative of this using integration by parts or some funky thing, but you can take a little shortcut here if you remember from calculus that if you have an odd function, i.e. a function such that f of minus x equals minus 1 times f of x, then if you integrate any integral that's centered at the origin will always integrate to 0 because the positive part and the negative part of the integral will cancel itself out. So here we can just look at this and say that it's 0 due to the fact that the integrand is an odd function without actually trying to pull out our old calculus books and frantically try to remember to how you integrate that thing if it's even possible. Oh, some examples of discrete random variables. Take a really simple random variable that just some sort of indicator function that's equal to 1 if a given event occurs, 0 if the event doesn't occur. It could be a coin toss, it could be getting a royal flush in a poker hand, doesn't matter what the actual event is, but the expected value of that particular event is going to be equal to 0 times the probability that the event does not occur, plus 1 times the probability that the event does occur, which ends up being, of course, just the probability that the event occurs, which agrees with our intuition. And if we have a binomial random variable, recall the binomial distribution, we'll be discussing this in more detail later, but binomial distribution is when you have an event that has some fixed probability of success, you repeat that event n times and you count the number of quote-unquote successes. I mean, simple canonical example would be like a coin toss. You toss a coin 6 times. What's the probability that you get 2 heads or 3 heads or whatever the case may be? Or more generally, if you have a weighted coin such that the probability of heads is p, then the probability that you get exactly x heads in n tosses will be this n factorial time over n minus x factorial times x factorial times p to the x times 1 minus p to the n minus x. So to find the expected value of this thing, we take this whole expression and multiply it by x, and that sum looks kind of ugly, but we can calculate it exactly doing a little bit of algebraic manipulation. That the x will cancel with the x and the x factorial, so we would be left with x minus 1 factorial in the denominator. Then we pull an n out of the n factorial, and we pull a p out of p to the x, and we end up with an n times p outside of the summation sign, and n minus 1 factorial times p to the x minus 1. And if you're looking closely here, you see this is just the density function for a binomial distribution with n minus 1 tosses rather than n tosses, and since it's a density function or probability mass function, I think is the term, that Cassell and Berger prefers. That sums to 1, so the expected value is just equal to n times p, which again should agree with our intuition that if the probability of getting ahead is p, you throw the coin n times, you would expect to observe about n times p heads. Here in a minute, I'll show you a slightly easier way to calculate this expected value so that you don't have to play these funny games with the summation and figure out what to pull outside the summation sign just to make this thing sum to 1. And another example of calculating the expected value of a discrete random variable. This time we're assuming x has a geometric distribution, which again I'll describe in more detail later. The intuition behind a geometric distribution is you keep tossing a coin until you get a heads, at which point you stop. What's the probability that it takes x tosses before you get your first head? So the probability mass function of that, in order for that to happen, you have to roll, first toss x minus 1 tails and 1 head. And the probability of tails is q, which is equal to 1 minus p. So we need x minus 1 of those and 1 p. So the probability that it takes x tosses to get your first head is going to be p times q to the x minus 1. At any rate, we need to find the expected value of that. So the formula for the expected value is going to be sum from x equals 1 to infinity of x times p q to the x minus 1. This is a little bit more complicated because in theory, if you were really unlucky, you could flip your coin 100, 1,000, a million, 10 Googleplex times before you get your first tail, or before you get your first head. So you have to sum over infinity here, and we have to try to make this infinite sum into something that we can actually evaluate. So how do we do that? Well, we can first notice that x times p to the q minus 1 could be written as p times the derivative of q to the x, because x times q to the x minus 1, of course, is just the derivative of q to the x with respect to q. And this step, more on this later, if you're a PhD student who attended the supplemental discussion section last week, this step should make you nervous. If we can pull this differentiation side outside of the infinite sum, then we're just summing from 1 to infinity of q to the x. Now, can we do this? I'll comment on this a little bit more here in a second. But for the time being, you can take my word for it, this is a legal operation. So now we're summing from 1 to infinity of q to the x, which, if you can remember studying infinite series from elementary calculus or analysis or any time that you've studied this, that is just a geometric series that sums to 1 over 1 minus q minus 1. Again, if you don't remember the geometric series, or if you've never seen this before, you can Google it, or you can just take my word for it. One way or another, that's equal to p times the derivative with respect to q of this particular expression, which, when we differentiate and simplify things, we end up with p over 1 minus q. 1 minus q is, of course, just equal to p. You end up with p over p squared, which is equal to 1 over p. And so, if you're a PhD student and interested in making sure that you understood the supplementary material from last week, in general, you cannot always move the derivative sign outside of an infinite sum like this. It only works if the series converges uniformly. in this case, you can show the geometric series does converge uniformly, so this this is a legal operation. But you can construct examples where if you move the derivative outside the summation side, then you end up with something that's not actually equal. So if you're an MS student, you can just forget what I just said because that doesn't concern you. But this is something that they want the PhD students in the class to at least have some knowledge of, that in general, you can't always move a derivative or an integral or a limit outside of a summation sign like that. It's only legal under certain conditions.
Do you mean by when you say that converges smoothly, I mean uniformly? Do you mean by that the sequence is within the L1 space?
Oh, wow, you're like, which L1 space specifically?
The L1 space where the norm, the p norm of the sequence is less than infinity.
I'm trying to remember. Where did you learn this? Jeez. I have vague memories of learning something like this way back in the day. The set of uniformly converging functions beat some sort of LP space something or another, but I can guarantee you that will not be on the exam in this class. If you're really curious, I can look that up, but I honestly don't remember. If you're really curious, I put some additional readings on Sakai about uniform convergence. If you're not doing the PhD problems, you don't need to worry about it, but it's there for your own edification. And it defines uniform convergence, but it doesn't talk about this LP space of uniformly converging functions, which I took functional analysis, but it was like 15 years ago, and I don't really remember it anymore. And little fun fact that I actually was not aware of until I prepared this lecture, but if you have a non-negative random variable, this only works if the random variable is non-negative. But you can show that the expected value can be calculated by finding the area under the survival curve, defined to be 1 minus the CDF. So to calculate the expected value, rather than taking x times the PDF, you can just take the integral from 0 to infinity of 1 minus the CDF for either the continuous or the discrete case. So, for example, if x is exponentially distributed with rate parameter lambda, as you'll recall, the CDF is 1 minus e to the minus lambda x for x greater than 0. So to get the expected value, we can just integrate that from 1 minus that from 0 to infinity, which of course is just equal to e to the minus lambda x, which is equal to lambda, consistent with the calculation that we got using the other method. Here's some examples of survival curves if you haven't taken survival analysis and seen this before. I have no idea where this graph came from. It was in the slides that was given to me, but apparently in this particular study, people who were depressed tended to die sooner than those who weren't depressed. The x-axis here is years of follow-up. The y-axis is the probability that you're still alive at a certain number of years of follow-up. So, for instance, 6 years follow-up, only about 65% of depressed men were still alive versus about 80% of non-depressed women. Oh. Now you know what a survival curve looks like for when you take that class. Wait. properties of expected values that are often useful from working problems and things like that. If you take what we call an affine transformation of an expectation that you multiply by a constant and add to a constant, then you can just take the expected value, multiply by a, add the constant without recalculating the expected value. Similarly, if you want to take the expected value of two different random variables and sum them together, that's just the expected value of the first random variable plus the expected value of the second random variable. If a random variable is positive for all x, then its expected value is positive, and if a random variable is bounded below by a and bounded above by b, then its expected value is in that range as well. All of these are trivially easy to prove using the properties of sums and integrals. There should be proofs in Cassell and Berger if you're really curious. And as an aside, the simple proof here for this second property, the sum, the expected value of the sum is just the sum of the expected values. The simple proof assumes they have the same distribution. We'll show later on that that property is true even if they don't have the same distribution. Oh, to show why these properties are useful, let's return to the case where we're finding expected value of a binomial random variable. And we'll do a simpler way of finding the expected value in this case. But first of all, we can observe that the binomial random variable can be expressed just as the sum of a series of independent binomial trials. These are also known as Bernoulli random variables, where you can think of it, I1 corresponds to the first toss of the coin, I2 corresponds to the second toss, I3 is the third toss, and so on. To the binomial random variable will just be the sum of all these individual tosses. Well, if we toss a single coin, the probability of success by definition is p, so the expected value of I is p for all possible i's. So since we toss n of them, the expected value of x is just the sum of the expected values of each individual I. So we're summing from I equals 1 to n of p, so the net result, we're just summing np's. The expected value is np. Same result that we got earlier, but we don't have to do the funky thing with figuring out what to pull outside the summation sign to get this result. And one interesting property of the expected value is that if we assume that all of these integrals exist, that if we want to find the value of b such that we minimize the expected sum of squared errors we could think of in a certain sense, we minimize the sum of the squared differences between x and b, the value of b that will minimize this quantity is precisely the expected value. In other words, when we could take our rolling the die example again, we want to find b such that we minimize 1 minus b squared over 6 plus 2 minus b squared over 6 plus 3 minus b squared over 6. We want to minimize that quantity. The value that would minimize it would be 3.5, i.e. the expected value. That you can think of the expected value minimizes the sum of squares between the all the possible observed values and the expected value. And I think I said that wrong, but hopefully that makes sense. It's, if you've ever been exposed to regression in the past, this is the same sort of idea here, where regression, you're trying to minimize the squared residuals, the difference between the predicted values and the actual values. Here, we don't have a y value that we're trying to predict. All we have is an x value, and we're trying to predict x based on the other x's. This tells us that what's consistent with our intuition, that the quote-unquote best prediction of x is just the mean of the x's, or the expected value of the x's. And probably seen this before, but in case you haven't, this quantity, the expected value of x minus e of x squared, is also known as the variance of x. And there's two different ways that you can prove this. I'm not going to go through either of them today. Simpler approach is you can just differentiate this with respect to b. That's a homework problem. It requires more assumptions in terms of being able to differentiate under the integral sign and all that. You can also do it using a sum of squares decomposition that doesn't rely on these assumptions. And another piece of terminology for something that comes up occasionally, honestly, you most often see this idea of moments in the context of moment generating functions that I'll discuss here in a moment. But if you have a random variable x, if you take the expected value of x to the r, for r equals 0, 1, 2, etc., these are known as the moments of x. So the first moment is just the expected value, the second moment, expected value of x squared, the third moment, the expected value of x cubed, etc., etc. Easy to show. The 0 at the moment is always equal to 1 because you're finding the expected value of 1, and the expected value of a constant is always that constant. M1 is just the usual expected value, frequently denoted by mu. And you can also define central moments as follows, where rather than just taking the expected value of x to the r, you take the expected value of x minus e of x to the rth power. I mean, you usually don't. Well, the second expected moment, of course, is the variance, and people use that all the time. But other than that, I don't see central moments used that much, but I'll describe them briefly just in case you ever see them. Once again, the 0th central moment is equal to 1 because taking expected value of 1. The first central moment is 0 because that reduces the expected value of x minus expected value of x, which is of course 0. Second central moment is just the variance. Third and fourth central moments are related to the skewness and kurtosis, which are sometimes useful, I guess. But otherwise, I can't think of a whole lot that you would ever use these for. As I said, the second central moment is called the variance. It's usually denoted by sigma squared. And it's by definition expected value of x minus mu squared, where mu is just the expected value of x. And if you do the algebra, you can show that that's equal to the expected value of x squared minus mu squared. And a couple comments on this. You can show fairly easily that if you want to find the variance of ax plus b, the same sort of affine transformation thing, the b doesn't make any difference at all. If you add b to a random variable, its variance doesn't change one bit. And that should make sense intuitively. The intuition behind the variance is that it measures the dispersion of a distribution. Distribution with low variance, all the values are clumped together close to the mean. Distribution with high variance, all the values are spread out a lot. If you just shift it to the left or to the right, that doesn't change the dispersion at all. But if you multiply at the expected value by a constant, then that does change the variance by a factor of a squared in this case. And it's also worth pointing out that expected value of x squared with the squared inside the parentheses is not the same thing as the expected value of x close parentheses squared. In fact, you can prove fairly easily that the first quantity is always greater than or equal to the second quantity because the variance is always greater than or equal to 0, and they'll only be equal to one another if the distribution has 0 variance, implying that it's just a point mass at a single point, and that it's equal to some value y with probability 1, and the probability of taking any other value is 0. And in any other case, the variance will be positive, and the expected value of x squared with the squared inside the parentheses will be strictly greater than the expected value of x squared with the squared outside the parentheses. And skewness, you may have seen in the past if you've taken statistics before, is defined to be the third central moment divided by the second central moment to the power 3/2. Quite honestly, why they defined it that way, I'm not 100% sure. I mean, the third central moment does give you some idea of the symmetry of the distribution, that if it's 0, that implies the distribution is symmetric. Positive implies right skew. Negative implies left skew. And that's all fine and good, I suppose. Why it was necessary to divide that by the variance raised to the 3/2 power, I quite honestly have no idea. But skewness. Worth knowing what they're talking about in case you ever see it again, I guess. And it's possible to write the central moments as a function of non-central moments and vice versa. For example, if mu2 is the second central moment, i.e. the variance, as I said before, that's the variance is equal to expected value of x squared, which is of course the second moment or second non-central moment minus expected value of x first moment squared. You can define the third central moment a function of the skewness likewise. I'm not entirely sure why you would ever want to do that unless it's a part of a homework problem, but anyway. So let's show how this method of indicators can be useful again for computing a variance. Let's say that we wanted to find the variance of a binomial distribution. Well, again, recall that the binomial distribution of where you're tossing a coin n times, that would be equivalent to where you just toss a coin once. You define a random variable II to be the result where you toss a coin once and then repeat that particular event n times. So, expected value of II, the probability of getting the expected value of a single coin toss is just the probability of getting ahead, and probability of II squared is the same thing, because that random variable takes on the values either 0 or 1. So the expected value of II squared is just the expected value of II, which is equal to P. And the variance of II is going to be equal to the expected value of II squared, i.e. P, minus the expected value of II, quantity squared. So in other words, P minus P squared, or P times 1 minus P. So to find the expected value of x squared, this time where x is binomial distributed, that's going to be the well, first of all, we're going to compute the expected value of x squared for the binomial distribution, which will be the expected value of the sum of these individual II squared, which, if you FOIL all that out long term, that's going to be the expected value of the double summation of II times ij. And we can break this inside part into two pieces. First of all, the piece where II equals II, and that ends up being II squared, which is just II because that's a 0, 1 random variable, plus II times ij for when they're not equal. So there's n of those, and each of those expected values is going to be equal to P. And there's going to be a total of n squared minus n of these, n squared total terms minus these n terms here, times the expected value of II times ij, which is P squared. The intuition there is that II times ij is equal to 1 only if II and ij are both equal to 1, and the probability of that is just P times P, or P squared, so we end up with n times P plus n squared n times P from the n P's, and n squared minus n, so there's a total of n squared minus n of these terms, times P squared. So to get the variance, we just take this quantity, np plus n squared minus n times p squared, minus the expected value of x, which we already know is n times p squared, which, when we write it all out, ends up being n times p times 1 minus p. Well, does that all make some semblance of sense? I know the algebraic manipulations here are a little bit odd, but the details aren't that important. It's just illustration of the type of tricks you can do to calculate these sorts of things. And the title of the slide here is a little bit rhetorical. Can moments not exist? Obviously, the fact that I'm showing you this example is because there are situations where they may not exist. Famous example of this is the Cauchy distribution, as I alluded to last week, that's famous for being a distribution that's kind of bell-shaped like the normal distribution, but has much larger tails than the normal distribution. So, how do we calculate the expected value here? That the mean in this case would be integral from minus infinity to infinity of x times 1 over pi times 1 plus x, 1 over 1 plus x squared dx. I mean, you might think, that's an odd function, that's equal to 0. What's the problem here? Well, it's a little more nuanced than that. Let's say that we, rather than trying to take advantage of this little odd function gimmick, what if we split it up into the positive and negative pieces like this, and calculated the antiderivative for those two pieces separately? And using the fact that it's an odd function, we can just rewrite this piece as the integral from 0 to infinity of 1 over pi x over 1 plus x squared. And you'd want to say, well, you're subtracting something from itself. That's just 0, right? Well, not so fast. If we actually integrate half of this thing, then we end up with an antiderivative 1 over 2 pi log 1 plus y from 0 to infinity is equal to infinity. This expression turns out to be infinity minus infinity, which, if you've taken calculus, you know is undefined. So, technically, and this just occurred to me right now after I'd already created the slides, I don't know if this may be beyond the scope of this course, but at least if you're taking 760, this is worth knowing. Formally, the expected value is only defined to exist if this integral from minus infinity to infinity of the absolute value of x times 1 over pi 1 plus x squared is less than infinity. If that integral is equal to infinity, as it is in the case of the Cauchy distribution, then the expected value doesn't exist by the convention. The reason that we say the expected value doesn't exist in that case is kind of convoluted. Hopefully it will make more sense by the end of this course, but later on in this course we'll prove something called the law of large numbers, which says basically if you sample a large number of things from the same distribution and divide by the sample size as the number of samples goes to infinity, that mean value gets closer and closer to the expected value. If you do that for the Cauchy distribution, this will never happen, because you can actually show that the mean of like 100 Cauchys is just another Cauchy. It's like, if you take in basic statistics, you know, like you take the mean of a bunch of normal distributions, you end up with something that's normal with the same mean, but smaller variance. The variance keeps getting smaller and smaller. The data gets packed closer and closer to the mean, so you take the average of a bunch of normals, you get closer and closer to the mean. Cauchy doesn't matter. If you take the mean of 1,000 Cauchys, 1,000,000 Cauchys, it's just exactly back where you started. The variance doesn't decrease at all. So you don't get closer and closer to the mean as the sample size goes to infinity.
Is it a general rule that the variance is finite if the expected value is finite and that the variance is infinite?
No. The canonical example of that, the t distribution, I think it's the t distribution with 2 degrees of freedom. It's a t distribution with a small number of degrees of freedom. I think it's 2, that it has a finite mean but infinite variance.
And how about in reverse? If it has an infinite mean, does it have infinite variance, or is that?
Yes. So that's the reason that we say that the expected value of the Cauchy distribution doesn't exist, and why we require this condition that the expected value of the absolute value of x be finite in order to say that the expected value exists, because if we don't have that condition, then that would imply that the Cauchy distribution has an expected value, but we say the expected value of the Cauchy doesn't exist because the law of large numbers doesn't apply for the Cauchy distribution. Another reason that you would want to say that the expected value of the Cauchy distribution is undefined is because it has infinite variance, that if you try to calculate the expected value of x squared, of course, the integral from minus infinity to infinity of x squared times 1 over pi times 1 plus x squared, you do all the manipulations to calculate the antiderivative and end up with 1 over pi from minus infinity to infinity of 1 minus the integral from minus infinity to infinity of 1 over pi times 1 plus x squared, which of course is just the density function for the Cauchy, so it integrates to 1. This integral is, of course, infinite, so the Cauchy distribution has infinite variance. Although, as I said, it's possible for a distribution to have infinite variance but finite means. The only example I can think of that off the top of my head is the t distribution with 2 degrees of freedom, but these examples do exist. So now we're going to shift gears a bit to moment generating functions. That moment generating function of a random variable is defined to be the expected value of e to the tx, where t is just some parameter, and moment generating function is said to exist as long as this expected value exists in some neighborhood around 0. It can be a small neighborhood, but it has to exist at 0 and at some neighborhood around 0. And the reason it's called a moment generating function is that if you want to calculate the nth moment of a random variable x, what you can do is just differentiate the moment generating function n times with respect to t, and then evaluate the moment generating function at t equals 0. That will give you the nth moment. So, I mean, that's probably the first question that you have when you see something like this, is why on earth would we ever care about something that convoluted? Well, the first answer is that sometimes calculating this nth derivative can be a heck of a lot easier than calculating some huge integral to, if you needed to know the 10th moment or something like that, or if you needed to know all the moments or prove that all the moments exist, sort of thing. So it may be, if you needed to calculate all of the other moments, it may be easier to just calculate the moment generating function and then do this differentiation to calculate all the remaining moments. The more complicated answer, which is actually the real answer, is that if you want to prove certain properties of an underlying distribution, you can prove things about the moment generating functions, and you can prove things about the moment generating functions and make your life a lot easier than if you were working with the raw distribution. That, in particular, if you've taken statistics before, you're probably familiar with the central limit theorem, which says roughly that if you take an average of a bunch of things, unless you deliberately choose some really horrible thing, that average of things will become normal after a while. And the standard proof of the central limit theorem uses moment generating functions that can basically show that the moment generating functions become approximately the moment generating functions of the normal distribution for n becomes large for a wide variety of distributions. So that's why we care about these things, that they can make proofs like that much simpler, in particular like the proof of the central limit theorem, arguably the most important theorem in all of statistics. Well, very quick aside, I don't want to go too far off on a tangent. For a moment generating function to exist, as I'll discuss later on, it requires that all moments exist, which is a very strong assumption. Oftentimes with the proofs you'll want to use characteristic functions instead, which I'll discuss on Thursday, which are guaranteed to exist even if not all moments exist. But for the time being, that's just an FYI, store it away in the back of your brain until Thursday. So, why does this formula on the previous slide apply? Well, if we assume that we can interchange the expectation and differentiation, which of course involves either an infinite sum or an integral, which hopefully if you're a PhD student by now, you've learned by now that's not something that's automatically legal. But if we're working with a distribution such that this is legal, then if we take the derivative of the moment generating function and take this derivative inside the expectation, i.e. inside the integral or the summation, that's going to be, if we differentiate once, that's going to be expected value of x times e to the tx evaluated at t equals 0. It's just the expected value of x. Similarly, we differentiate twice, that's the expected value of x squared times e to the tx, which of course is just equal the expected value of x squared, etc., etc. Another way that you can see this is to do a Taylor series expansion. If you recall from your calculus days that the Taylor series for e to the tx is going to be equal to 1 plus tx squared over 2 plus tx cubed over 3 factorial plus tx to the fourth over 4 factorial, etc., etc. So that's going to be equal to the sum from 0 to infinity of t to the n times the expected value of n over n factorial. We differentiate this expression, say, j times. The first j minus 1 terms go to 0. The remaining, the jth term has no t coefficient. All the others still have a t. So we evaluate that at t equals 0. Only the jth term remains, which is precisely the expected value of x to the j. So now a couple examples of how you would actually calculate these moment generating functions. Let's take an exponential random variable. We want to calculate its moment generating function. Well, that's expected value of tx, which using the formula from the beginning of this lecture, that's just the integral from 0 to infinity, e to the tx, the thing that we're finding the expected value of, times the density, lambda times e to the minus lambda x. Pull lambda out of the integral sign, that's just integral from 0 to infinity of e to the minus lambda minus tx times dx. And we can easily compute the antiderivative of that. It's minus 1 over lambda minus t, and ends up being lambda over lambda minus t. Note this integral is only finite if t is less than lambda, otherwise it's infinite, but no big deal, because we only need the moment generating function to be defined in a neighborhood around 0, and the neighborhood around 0 will be less than lambda. We can find such a neighborhood no matter how small lambda is, so we're good. And so if we want to find the moments, if we want to find a formula for all possible moments of an exponential random variable, the easiest way to do this is with the Taylor expansion idea again. First, we take this expression, divide both the numerator and the denominator by lambda, and by the Taylor series expansion from the earlier slide, that's going to be equal to, actually, take that back, I can't remember my own notes. This step here follows from the fact that the sum of a geometric series of t over lambda, the sum of that geometric series is just this. So then we use the Taylor series expansion from the previous slide, and we see that expected value and set the various terms equal to one another, we end up with the expected value of x to the n is going to be equal to n factorial over lambda to the n, because you see the coefficients for these two infinite series are identical, except for the lambda to the n and the n factorial on the bottom. So that implies to get the two series be equal, expected value of n has to be equal to n factorial over lambda to the n. So by calculating this one integral, we now have a formula for all possible moments of an exponential random variable. Kind of cool. And so in particular, that gives us the expected value of x is 1 over lambda, and the variance of x is 1 over lambda squared. So now let's do the same thing for a discrete random variable. Let's say we want to find the moment generating function of a geometric random variable. Recall, this is the random variable where you keep flipping a coin until you get a heads. So here we need to find the expected value of e to the tx, which, since it's discrete, this is going to be a sum rather than an integral. The sum from x equals 1 to infinity of e to the tx times the probability mass function, which can be written as p divided by q times the sum from x equals 1 to infinity of q e to the t to the x power, which that's just another geometric series. That sum can be written as 1 over 1 minus q e to the t minus 1. Simplify that out, we get p e to the t over 1 minus q e to the t is the moment generating function. And once again, this will converge if and only if e to the t times q is less than 1, or if t is less than log 1 over q. Again, this only needs to be defined in some neighborhood around 0, and no matter how big or small q is, well, unless q is equal to 1, this will blow up, but for any q, or 0 for that matter, but any q between 0 and 1, we can find a t such that that's true, so the moment generating function exists. And if we want to find the moments of the geometric random variable, we can just differentiate this thing, take the derivative of the moment generating function with respect to t evaluated at t equals 0. Once we do the calculus and the algebra and simplify everything, we end up with 1 over p, exactly the same expected value that we got when we did this the other way. Some other properties of the moment generating function is that if you do an affine transformation of a random variable, then the moment generating function of that affine transformation will just be e to the bt times the moment generating function evaluated at at. Proof is fairly straightforward. Expected moment generating function of ax plus b evaluated at t is just the expected value of e to the t times ax plus b, which is of course e to the expected value of tax times e to the bt. E to the bt is a constant. We can pull it out of the expectation sign, and expected value of e to the at times x, that's precisely the definition of the moment generating function evaluated at a times t. So one final example, let's say we're trying to find the moment generating function of a Gaussian random variable. As I said, this is an important example because this gets used in the proof of the central limit theorem. The moment generating function in this case is e to the tx times e to the minus x squared over 2 divided by 2 pi. So pull an e to the t squared over 2 term outside the integral sign because it's constant with respect to x, and this can be written as just the integral from minus infinity to infinity of e to the minus x minus t squared over 2 for 2 pi. And that's just the density function of a normal random variable with variance 1 and mean centered at t. Since it's a density function, it integrates to 1. That gives us that the moment generating function of a standard normal random variable is e to the t squared over 2. And now, if we expand that as a Taylor series, that tells us the Taylor series for e to the x is their question.
Oh, I was on the PDF of the normal distribution. Isn't it square root of 2 pi?
You're right. That's an embarrassing typo. Well, I'll try to fix that and update a new version. But at any rate, if we take the Taylor expansion for e to the t squared over 2, that's going to be equal to sum n from 0 to infinity of 1 over n times t squared over 2 to the nth power, which we simplify, that's t to the 2n over 2 to the nth power times n factorial, which is equivalent to just summing over the m's that are even of t to the m over m factorial times 2 to the m over 2 factorial, m factorial in the numerator. So if we do the same trick that we did on the previous slide, where we match coefficients of t to the m over m factorial to the general Taylor expansion for e to the tx, that gives us that all the odd moments are 0 because this term is only non-zero when n is even, and the even moments, e to the xm, are just m factorial divided by 2 to the m over 2 times m over 2 factorial. So now we can calculate all the moments of the normal distribution. And one final little comment that if we want to find the moment generating function of a normal distribution with mean mu and variance sigma squared, we can just use the formula from the previous slide to find a random variable y to be mu plus sigma times x. And that gives us the moment generating function of this new y is just e to the mu t plus sigma squared t squared over 2. And, well, I'm getting better at timing the lengths of these lectures. Any questions about anything today? On Thursday, I'll finish the discussion on moment generating functions. I will probably finish early and spend the rest of the time talking about Taylor series for the 690 students, as we did last week.
For this, are you just evaluating that?